In this video, we're going to learn how to do differentiation involving exponential and logarithmic functions. That means we're now interested in finding the derivative of a to the power x and log x with base a. For the functions to be well defined and differentiable, throughout this video we assume that a is positive and not equal to 1. In order to do these differentiations, first of all, we should take a look at a special case, which is the derivative of natural log of x. Now we can try to do this differentiation from first principles. And before we do that, we must recall that we have learned this limit, that is the limit of 1 plus x over n to the power n as n approaches infinity is equal to e to the power x. From this result, we can derive that the limit of 1 plus ux to the power 1 over u as u approaches 0 should be also equal to e to the power x. Now we can consider first principles. D log x with respect to x is equal to the limit of log x plus delta x minus log x over delta x as delta x approaches 0. By the properties of logarithms, we have learned that log a minus log b is equal to log a over b. And then for the factor here, it can become the power here. After that, x plus delta x over x can be rewritten as 1 plus delta x times 1 minus x. And then we can take limit of this expression inside the logarithm like this. Now when we compare these two results, we can see that this limit should be equal to e to the power 1 over x. Therefore, after taking the natural logarithm, it is just equal to 1 over x. So that's our first formula, that is d natural log x dx is equal to 1 over x. After knowing this result, we can now try to differentiate e to the power x. Of course, we can do this differentiation from first principles, but now let's try to make use of this result to do this differentiation. First of all, we can let y be e to the power x. Then we can take natural log on both sides so that log y is equal to x. After this, we can differentiate both sides with respect to x. For the left hand side, d log y dy is equal to 1 over y. And then by chain rule, we should multiply dy dx here. And then dx dx is just equal to 1. After solving for dy dx, we can get that dy dx is just equal to y. But y means e to the power x, so we can conclude that d e to the power x dx is equal to e to the power x. That means it is equal to itself. That is our second formula, that is d e to the power x dx is just equal to e to the power x itself. Please note that in this example, we do not find dy dx directly. Instead, we try to take log on both sides, and then we do the differentiation, and then afterwards we solve for dy dx, and then afterwards we substitute e to the power x back into y. This kind of differentiation is known as the logarithmic differentiation. That means instead of doing the differentiation directly, we try to take log on both sides, and then we differentiate both sides. Afterwards, we can take a look at the general case of differentiating logarithms. To differentiate log x with base a, since we have already learned how to do the differentiation for the natural logarithms, we can try to change the base of this logarithm so that it is in base e, and it is the formula of changing base in logarithms. Now because this denominator log a is a constant, that means we can take out 1 over log a like this, and then we have already learned how to do this differentiation. Therefore, it is equal to 1 over log a times 1 over x. In other words, it is equal to 1 over x times natural log a. And that's our third formula. After that, we can take a look at how we can differentiate a general exponential function a to the power x. Again, the trick is to change the base from a to e. And to do this, we can consider a to be equal to e to the power natural log a. And therefore, we just need to differentiate e to the power x log a with respect to x. And then we can do this differentiation by chain rule. For the first differentiation, because it is just equal to itself, so it is equal to e to the power x times log a. And then for the second differentiation, it is equal to log a. And then here, we already learned that this one is just equal to a to the power x. And therefore this term can be rewritten as a to the power x, and that's our fourth formula, that is dA to the power x dx is equal to a to the power x times natural log a. Now let's take a look at some examples and see how we can apply these formulas to do differentiation. In the first example, to find dy dx, we should apply the product rule. That means we first of all take out x squared and then we differentiate this. And then to do this differentiation, we apply the chain rule. And then for the second part, we take out e to the power 2x plus 1. And then we differentiate x squared. And then for this differentiation, it is just equal to itself. And then for this differentiation, it is equal to 2. And then for differentiating x squared, it is equal to 2x. As a result, after taking out the common factors, it is equal to 2x times e to the power 2x plus 1 times x plus 1. Next, in the second example, we need to find dy dx when y is equal to natural log of 1 plus x minus x squared to the power 3. In this case, instead of doing differentiation directly, we can consider put this power 3 in front of log like this, so that the power is smaller. And the rule of thumb is that if the power is smaller, then the differentiation is easier. Now we can find dy dx. As this 3 is a constant, we can just take it out. And then to differentiate this natural log, we should apply the chain rule. For the first differentiation, it is just equal to 1 over this. And then for the second differentiation, it is equal to 1 minus 2x. As a result, it is equal to 3 times 1 minus 2x over 1 plus x minus x squared. Next, let's take a look at this example. In this example, this is a common logarithm. That means the base is equal to 10. And that means a is equal to 10. And therefore, to do this differentiation by applying the chain rule, this part should become 1 over 3 minus 5x times natural log of 10. 10, that means the base here. And then for this part, it is equal to minus 5. Therefore, this is the result of the differentiation. Next, we can take a look at this example. Again, in this case, to find dy dx, we can apply the chain rule. And then by referring to this formula, the first differentiation becomes itself times natural log of 3. 3 means the base here. And then for the second differentiation, it is equal to 5x to the power 4 minus 8. And therefore, this is the result of the differentiation. Finally, let's take a look at this example. Let's see how we can differentiate x to the power x. Please note that we cannot directly apply this formula, because in this formula, this a is a constant. But here, this x is not a constant, so we cannot directly apply the formula. In fact, in this case, we cannot do differentiation directly. Instead, we should first of all take log on both sides, so that the left-hand side becomes log y, and the right-hand side becomes x log x. Now we can differentiate both sides to find dy dx. For the left-hand side, after differentiation, it is equal to 1 over y times dy dx. And then for the right-hand side, we should apply the product rule. That means we should first of all take out x, and then we differentiate log x so that it is equal to 1 over x. And then for the second part, we should take out log x, and then we should differentiate x so that it is equal to 1. And after simplification, it is equal to 1 plus log x. Then we can solve for dy dx, and we should know that dy dx is just equal to y times 1 plus log x. But we know that y is equal to x to the power x, so we can substitute this back into y. And therefore, dy dx is just equal to x to the power x times 1 plus log x. So that's how we can do differentiation in this special example. And please be reminded that this special technique is known as logarithmic differentiation. That means instead of finding dy dx directly, we first of all take log on both sides and then we differentiate both sides, and that's called the logarithmic differentiation. So that's how we can do differentiations involving exponential and logarithmic functions.